Our next speaker is Rachele Anderson from Lund University, and she will be talking about optimal time frequency feature extraction for classification of EEG signals. Please, Rachele, thank you. Go ahead.
Thank you. So, hello, everyone. I'm going to talk about how to obtain optimal time frequency representations that can be used for classifying EEG signals. I will start with a little introductory background, recalling the difference between stationary and non-stationary spectral analysis. Then I will introduce you to a model for non-stationary signals called locally stationary processes, for which we can obtain a mean square error optimal time frequency estimate. We will see how to use this in practice by estimating the model parameters from data and obtain optimal multi-tapers and their weights. Finally, I will present an evaluation of this approach in comparison with other state-of-the-art time frequency estimators in terms of mean square error and then in terms of classification accuracy, both for classifying simulated data and also in a real EEG data case, where the EEG data is measured during a memory encoding task. So let's recall the definition of stationary stochastic processes. We say that a stochastic process is stationary in the wide sense if its mean function is constant and its autocovariance function depends only on the time lag, so only on the time distance between points. These properties are nice, and they have been used a lot in statistics and time series analysis. For example, models such as autoregressive models or moving average models are for stationary data, and they work well, especially if the data has been cut in shorter segments. But in practice, these characteristics are too limiting, since most real signals exhibit changes in their statistical properties over time. For stationary signals, the power spectrum of a time series describes the distribution of power into the frequencies composing the signals, and is defined as the squared absolute value of the Fourier transform of the signal. For non-stationary signals, we are interested in the changes in the frequency content of the signal. So stationary spectral analysis is not sufficient, and that's why time frequency analysis is one of the main tools for analyzing non-stationary signals. EEG signals are an example of non-stationary signals. On the left, we have the diagram of the International 1020 system for electrode placement, and on the right, we have the actual data consisting of measurements from 31 electrodes recorded during one trial of a memory encoding task. Even if the measurements are very noisy, you can see that the data is non-stationary, since a transient shows up about 200 milliseconds after time zero, that is the time when the visual stimuli has been presented. For non-stationary signals, there is a natural extension of the Fourier transform, and that is the short time Fourier transform, where a window function h allows to consider shorter subsequences of the signal. The spectrum is then defined as the square magnitude of the short time Fourier transform. The spectrum shows how the spectral density of a signal varies with time, and the result is a picture that has dimensions time, frequency, and the square magnitude. Even if the spectrum is very often used in applications, it's far from being ideal, since the ideal time frequency representation is a distribution that satisfies a list of conditions. This is why the Wigner-Will distribution has become popular in time frequency analysis, since it satisfies most of the properties that are expected from an ideal time frequency representation. In this table, you can see a comparison of the requirements satisfied by the Wigner-Will distribution and by the spectrum. Here we have an example. So we have a signal with 3 Gaussian components located at different time and frequency. The second plot is the spectrum, and the third plot is the Wigner-Will. You can see that the Wigner-Will distribution gives better time frequency concentration. But if the signal has different components, as in this case, the Wigner-Will distribution suffers from the so-called cross terms that are located in between the actual signal components, and that can be twice as large as the outer terms. To reduce these cross terms, one can use a proper time frequency kernel. These kernels are usually designed in the ambiguity domain because outer terms and cross terms relocalize in a beneficial way, since the signal outer terms will always be located at the center and the cross terms will always be located far away from the center in the ambiguity domain. Here we have the definition of the ambiguity function and how a filtered ambiguity function can be obtained by multiplication with an ambiguity kernel. The corresponding time frequency kernel can be computed and then used to obtain the smoothed Wigner-Will distribution as the 2-dimensional convolution of the Wigner-Will and the time frequency kernel. We extend these concepts to the stochastic case by introducing the instantaneous autocorrelation function. We can define the Wigner-Will spectrum and the ambiguity spectrum. Since the expected value computed from just a few realizations or just one realization of a process is very unreliable, being able to compute a reliable time frequency spectrum from a few realizations is one of the main challenges in time frequency analysis. Now I'm going to introduce a non-stationary stochastic model for which we can explicitly derive the mean square error optimal kernel. The model is known as locally stationary process, and it has been introduced by Silverman in the 50s. It's based on the modulation in time of an ordinary stationary covariance function. Formally, we say that a zero mean stochastic process X is an LSP if its covariance function can be written as the product of 2 functions Q and R, where Q is a non-negative function representing the varying instantaneous power, and R is a normalized stationary covariance function. Clearly, not every choice of function is suitable, since the product must be a covariance, and that means that it must be positive semi-definite. Let's talk about the estimation of the Wigner-Will spectrum of an LSP. The general theoretical expression of the mean square error optimal ambiguity kernel has been derived by Said and Jones in 1995. And thanks to the convenient expression of the Wigner-Will spectrum and the corresponding ambiguity kernel for LSPs, Valberg and Hansson-Sansen computed the optimal kernel for LSPs, where the factors are Gaussian functions. How do we use this in practice? So, especially for EEG. Well, this is a post-Simon model for EEG, which we have applied to EEG data. The parametric function Q and R are 2 Gaussian functions, or Q a Gaussian function with also a minimum energy level to lift it, which could be possibly underlying noise. Then we have a parameter AQ, which represents the amplitude, a parameter BQ that is the time of maximum energy in the process. And then we have two parameters, CR and CQ, that rule the relationship between the local stationarity and the time-dependent behavior. And we need that CR is larger than CQ to assure that the result is a positive semi-definite covariance function. Let's look at a few realizations simulated from the model. And we can see how the realization looks different depending on the parameters. So each set of the displayed realization has the maximum energy located in the middle of the time interval, so at 0.25. But the relation between the two functions Q and R gives a slowly varying behavior in the first one, in A, and a much faster variation in B and C. The only difference between B and C is in the noise parameter L. So you can see how this L can be used to modeling additive noise in the time varying signal. Now that we have introduced the model for EEG, we can derive the optimal mean square error kernel for it. So the results that we have seen before can be extended for our model. And after some computation, this is how the kernel looks like. For practical applications, we need the method to make reliable parameter inference from the measured data. We addressed the lack of suitable methods for estimating the parameters of the LSP model by proposing a novel inference method based on the idea of dividing the inference problem into two simpler subproblems. So we could take advantage of the individual structure of the two parts of the covariance. So the matrix capital Q corresponding to the function Q, which is a non-negative Hankel matrix, and the matrix capital R that corresponds to the function R is a symmetric Toeplitz matrix. Here the algorithm is summarized. The first step is estimating the mean instantaneous power from the data using the realizations that we have. And then we find the set of parameters that define the function Q by fitting the parametric expression to the estimated P. Then we are able to use the fact that the matrix R is a stationary covariance, and then use all the points that have the constant distance, because we have already estimated Q. And finally, we find the parameters defining the function R by fitting the parametric expression to the anti-diagonal elements of the matrix, since they contain all the information, since it's a Toeplitz matrix. We could also compute the covariance matrix, the covariance estimate from this, but it's not what we are interested in now. We just want the parameters. Thanks to the inference method just introduced, we can compute the optimal kernel for real data. The efficient implementation is based on multi-tapers, from which we obtain a weighted sum of Windows spectrograms with weights alpha k and Windows hk. The weights and the windows are derived from the solution of an eigenvalue problem. And we have an efficient solution from an implementation point of view if just a few of these alpha are different from 0. Here, a plot to show how the multi-tapers and the weights can look like. So this is the result for a specific choice of parameters. So now we have a complete procedure for mean square error optimal spectral estimation for LSPs. And we know how to apply to real data. We start from model decision, then we do statistical inference on the model parameters using the inference method HATS. And then we derive the mean square error optimal multi-tapers, and weights, from which we can obtain our optimal time frequency representation. Now we want to evaluate the method. First, we want to see if we want actually to confirm this is the mean square error optimal estimator by comparing the mean square error in a simulation study and compare the method with other state-of-the-art time frequency estimators. Then we also want to see if using the optimal time frequency representation for feature extraction leads to an improved classification accuracy. And we will do this both in a simulation study and for the real EEG data. The time frequency estimators considered are the single Hanning window spectrum, HAN, and the Welch method with the 50% overlapping Hanning windows. Then we take the classical Wigner-Weil spectrum estimate and the wavelet transform using the Morlet wavelet. For allowing a comparison in a mean square error sense, the time frequency image is reconstructed from the scaleogram obtained with the wavelet using a standard relationship between scale and frequency. And for a fair comparison between all the methods are optimized. So we want the best mean square error that each method can give. So we optimize the window length for the spectrum, the number of windows for Welch, and we have a magnitude scaling parameters for the other two methods. In this figure, we have the box plots of the mean square error achieved with the different methods in 100 independent simulations. You can see that the spectral estimate obtained using the LSP optimal kernels achieves the best mean square error, as expected. But it's also interesting to notice that using the true parameters, or those estimated with the inference method proposed, we obtain almost the same mean square error. To test how the number of realizations used to estimate the model parameters with hats affects the results in the time frequency domain, we studied the decrease of the mean square error of the spectral estimator based on parameter estimates computed with a different number of realizations M. In this figure, we have the resulting mean of the mean square error in blue and the confidence intervals. And yes, these are computed still on 100 independent simulations for each number of realizations used. We can see that it's best to use at least 20 realizations to compute the estimates. Now we come to the classification in a simulation study, and then in the real EEG data case. For the simulation study, we simulate three classes of signals using the same function R and different function Q. Just slightly different function Q, because you see that only the noise is constant, and then only the parameters AQ, BQ, and CQ vary. And also the center frequency. So we have a center frequency F0 and jittering frequencies of about 2 Hertz, plus minus 2 Hertz. By looking at the true Wigner-Weil spectrum of the simulated signals, we can see that the classes can be distinguished in the time frequency plane. But if we look at the random signals in the time domain, we are not able to distinguish them. They just look the same. And here I'm showing you the classes of EEG signals that we want to classify, where the measurements are taken when a person was encoding a memory that could be a face, so a visual, they had a visual stimuli that could be a face, an object, or a landmark. We use a feed-forward neural network to classify the signals on the basis of the time frequency features computed with the different spectral methods, where a feature is each time frequency point in the time interval 0.5 seconds after the visual stimuli, and the frequency up to 40 Hertz. The simulated dataset consists of 100 realizations for each class, and we take a random partition of 80 realization for training and 20 for testing the neural network, and we repeat this 10 independent times. And then we re-estimate the model parameters on these testing realizations. We do similarly for the real EEG data case, but we have only 60 trials per class. We use 40 for training the network and 20 for independent testing of the network. In these tables, we have the classification accuracy for each method. First, we have in the simulation study, and then for the real EEG data case. And we see that the proposed method outperforms the other approaches. Now, if you want to read more, you can check out the paper, Time Frequency Feature Extraction for Classification of Episodic Memory. I want to thank Ines Bramau and Mikael Johansson at the Department of Psychology at Lund University for data collection. And I want to thank you all for listening.
Okay, thank you very much, Rachele. Very, very interesting. I'm going to see if there are questions from the audience. But in the meantime, so I have several, but I'm not sure which one makes sense. Let's try with this one. So would you say this can also provide a very useful tool for like generating synthetic signals? So suppose you want to validate, for instance, pipelines for estimating connectivity from brain signals. So would you reckon that these models can probably represent like better models of what can be reasonable brain activity with respect to, for instance, autoregressive models, which are definitely simpler models? Thanks.
I'm not sure if I would say better, because I think I would like to test it first. But definitely, yes, it could be done. So this model can be used also for generating data.
Okay, yeah, this sounds also very interesting. In addition to what you've been doing, of course, which is very, very cool. No, okay. Okay, no. Okay. So I stupidly didn't take notes of my questions during your presentation. That was quite silly.
One thing that could be, I mean, one could think of is that this is using just one channel, and then I don't exploit at all the fact that we have several channels. And that's because the model is one-dimensional.
Thank you. That was actually what I was going to ask you. In fact, I briefly discussed that. Yeah. So all this was done just using one single channel.
Exact. And it was, but it was a channel that contains a lot of information, because it was on the back. It was O1. So since it was visual stimuli, we know that it's going to be a strong signal there.
Okay, and so you mean that you could like generalize to multiple channels, both parts, so both the simulation and the inference?
I don't know. I have not done it, but it's interesting to. Yeah, that would mean defining the model in a multidimensional case, and I I don't know how that works exactly.
Okay. Okay, I see. So these models are naturally defined in just in 1D.
We have a question for.
Yes, I have a question. There may be some noise because my neighbor are a little bit noisy. My whole neighbor is a little bit noisy, but let's try. Just actually 2 questions. One is, when you talk about multiple channel, you mean like you have 3 channels and you want to analyze each channel one at a time, or you can also think about estimating correlations among channels? Do you have an intuition on this? So to estimate also, for example, cross power spectrum and not only the power spectrum?
So I'm thinking now how one would define optimal kernels for estimating the cross power spectrum. It's certainly something that could be investigated, not done in this work, but we have some other work where we look at the phase between channels. So yeah, it is not the same, but possibly could be used still to be investigated.
So just to check if I understood correctly, because I didn't understood all the details, of course, from these slides, even though they were really great. You mean probably if you want, while to generalize to multiple channel is quite easy to do the math, it may be complicated to find the optimal mean square or kernel for the cross power spectrum. So you have to do some more math, probably.
For having the optimal kernel, yes.
Okay. Okay, perfect. And another more practical question, is this method fast computationally with respect, for example, to Fourier transform, or it requires more computational issue?
So if when computing the multi-tapers, one saves them, then they don't have to be recomputed every time. So it can become, yeah, it can take longer than just the spectrum, but the trick is just to save all the multi-tapers and always use them in the further computations.
Okay, thank you very much.
But it's not faster, just to say, because actually you do a step forward, a step more by computing these optimal kernels and multi-tapers.
Okay, thank you very much.
I think we have one more question from Andreas.
It's related to the previous ones. Very nice presentation. Too much math to follow and ask the question sensibly, but you could at least compare 2 different sensors so you can see whether or not you get the same information, because the experiment you have, you are looking for a rare event which doesn't show very well in the signal. And one very important question is whether or not this is spreading to the EEG in that sense is good, because you don't need to localize. It's clearly the activity from many things that gives the memory trace. So if you compare the information that you get, how different they are, the same calculations from 2 different sensors, so across the sensors, that could give you an idea whether or not you need to generalize. A related question to that, I would be very interested to apply this method to actually tomographic solutions and see whether or not you can actually extract something at the level of the sources rather than at the level of the signal, and then compare the sources and do the cross correlation of the source space. So any comments on that?
I thank you for the first suggestion, because yeah, that could be good to see if there is actually differences using other sensors. And I have no experience with the applications that you are talking about, but of course it could be interesting.
You basically have this, it's just like any other signal. A tomographic solution gives you a time series which has more unique, it represents something real than the signal itself, because the signal itself is a convolution from contributions from all over the brain. So it could be more ideal, I would say, for looking at the source representation rather than for looking at the signal of the EEG. Thank you, very nice talk.
Thank you.
Okay, thank you very much, Rachele. Once more, thank you. Very interesting work.